Hey guys, Alex here with Serious Goose Games. Welcome back to our Unity Tactics RPG tutorial. In the last video we created a super simple attack function, so now our little boxes can actually start killing each other. Today will be a little different. When you work on a project, it's good to step back every once in a while and clean things up. Because I'm not building these tutorials off a completed project and only recording and testing videos a few in advance, I sometimes look back and realize that there is a better way to do something. So we're going to go through and clean up all of our code today. Doing this regularly is going to help keep it clean and might even improve performance and fix potential bugs. So we're going to start out in our grid manager. The first thing we're going to do is fix up our variables a bit. So we've got our width, we've got our height, we've got a tile prefab we're spawning in. I'm going to move our map up here. So it won't show up in the inspector still, but it'll be grouped in here. That'll make it easier for us to see, okay, so all these variables are map settings. And we've got our value map, our move cost, and we're going to add a couple of new ones. So private float, this will be half width, and we're going to set this to be our width divided by 2. And then we're going to do the same thing with the height. Now, for materials, we're actually going to get rid of dark material. We're going to rename light material to just be tile material. Now inside generate grid, we're going to replace width divided by 2 by half width, and height divided by 2 by half height. Now we're going to move our tile script up. Because the tile script already gets the renderer, we can get rid of this line of code here. And what we'll do is we'll do tile renderer. And then what we'll do here is tile script tile renderer. And it's going to yell at us because it's not set to public. So we'll have to fix that. We'll do that after. And set to a new material. And right now, we have these two different materials to create our checkerboard. We don't need that anymore. We've got our terrain colors. So we're just going to assign it tile material to create the instance run. Next, we're going to create an int called index. And this is going to be equal to our y times our width times x, or plus x. Then we'll take this line, and we'll move that up under there. And we'll replace this with index. Help keep it easy to read. I'm going to move this line where we set the grid position down. And I'm basically trying to organize it so we've got instantiation, then we've got color, and then we've got the script properties. So the next thing we're going to do is have our normalized cost. And then we're setting the original color. And then we'll set the tile properties. So after we set the grid position, we're going to do tile script dot grid manager is equal to this. So it's yelling at us because we don't actually have a reference to our grid manager in our tile script. So when we get to that one in the refactor, we're going to add in that reference. I'm doing this because I don't want to bounce back and forth between all these scripts. I just want to kind of run through. We'll add in. If there's an error, I'll explain why. And it will go away once we get to the script associated with it. So I'm going to add in some comments just to show what's happening. We've got instantiate. Then we've got assign color. And then we've got assign properties. That's our generate grid. Now we want to modify get tile neighbors and make this more efficient because it's getting called constantly in our pathfinding, in our other various spots. So we have a list of neighbors, and we know that this list is never going to be bigger than 8. So we're going to pass in 8 as the size, and then we're going to create a tile reference under that. And this is going to be called center tile. And this is going to be equal to map tile position dot x tile position dot y. So now inside both of our for loops, we're going to do if x is equal to 0 and y is equal to 0, and we're going to continue. So we're going to skip that tile. Next, underneath this if statement, we're going to do if we're not including diagonals and x is not equal to 0 and y is not equal to 0, then we're going to continue. So that'll be our new diagonal check. If all of those are true, we're going to do neighbors.add map position x, position y. So we just got rid of a bunch of stuff and a bunch of unnecessary things. Because we're calling this function so much, we want it to be tight We want it to be clean. We don't want to clutter it with a bunch of extra stuff that we don't need to be doing. Next, we're going to kind of overhaul our Dijkstra's algorithm here. First thing we're going to do is change move tiles to a hash set. Next, we're going to modify this a little bit to make it slightly more safe. So inside this if statement, we're going to add another if statement. That's going to be not cost so far dot try get value neighbor out int prev cost, so previous cost, or new cost is less than the previous cost. Then we're going to do the cost so far neighbor equals new cost. We're going to enqueue the neighbor. And then we're going to change this if statement here. So we're going to get rid of this first half of the condition. If neighbor is not equal to start tile, and move tiles dot add neighbor. Then we're going to do neighbor dot in move range equals true. So we took that if statement, we combined a line from inside it into the condition, because if we can add the tile, this is going to return true and add it. Next, we're going to move on to the attack section. So after we create our attack tiles hash set, we're going to create a queue of type tile, called tile, and then int distance. So this is the queue that we have inside the for each loop, but we're moving it outside. Don't forget to use parentheses. And we'll name it the same thing, attack queue. And this is equal to a new queue of tiles and distances. So we can completely remove that. We also don't need to do this concat. We can get rid of that. So it's just tile origin in move tiles. And then we'll enqueue the origin. And then we're also going to enqueue our start tile. And then instead of starting at our origin, we're going to start at our start tile. And then down here, we're going to modify this. And what this is going to let us do is essentially get rid of the link namespace, along with modifications we're going to do to our path function, our A star. So we're going to create a list of tile called result. And this is going to be equal to a new list of tiles. And the size is going to be move tiles.count plus attack tiles.count. We're going to do result.addRange attack tiles and result.addRange move tiles. And then we're going to return the result. So it's a little more code, but by changing things to like the hash sets and making sure we're telling it how big the list needs to be, we're doing some micro optimizations, which will help in the long run. Now we're going to go to the vector 3 version of getTile. And instead of having these offsets, because we already have those calculated as global variables, instead of offset X, we can replace that with half width. And instead of offset Y, we can replace that with half height. So we're not creating variables that aren't necessary. Now, before we move on to getPath and clean up our A star, we actually need to go back to Unity and we're going to create a new script. So right click, create model behavior script, and we're going to call this priority queue. So if you're familiar with C#, you should already know what a priority queue is. Unity does not have them built in, but they're really nice because they allow us to essentially create a list that is automatically sorted. So the first thing we do is get rid of model behavior. This is not something we attach to a game object. So we can get rid of start and update. And then it's going to be priority queue. We're going to give it a type where T uses the iComparable interface. Next, we're going to create a private list, type T, called data. This is equal to a new list of type T. And it's yelling at us. Instead of that, we want to use using system.collections.generic. Now we're going to create a public int called count. And that's going to return data.count. And we're going to create a public void called enqueue. We'll pass in T item. We're going to start out by doing data.add. item. Next, we're going to do int child index equals data.count -1. And then while our child index is greater than 0, then we're going to create an int called parent index. And this is equal to our child index -1 divided by 2. And then we're going to do if our data at our child index, and then we'll do dot compare to data parent index is greater than or equal to 0. Then we're going to break. And below that, we're going to do data at our child index, and then our data at our parent index is equal to our data at our parent index, and then data at our child index. So we're basically swapping the data. And then below that, we'll set CI, or child index, to be equal to parent index. Next, we're going to do kind of the opposite. We're going to dequeue. So public t dequeue. Inside here, we're going to do int last index. And this is equal to data.count -1. And we're going to do t called front item is equal to data at index 0. Then we're going to set data at our index 0 to be equal to data at our last index. Then we're going to do data.remove at last index. Next, we're going to create an int called parent index. We'll start that at 0. And then while true, we're going to create an int for child index. And that's going to be equal to our parent index times 2 plus 1. And then we'll do if child index is greater than or equal to data.count, we're going to break. Next, we're going to create an int called right child. This is going to be equal to our child index plus 1. Next, we're going to do if our right child is less than data.count and our data at our right child dot compare to our data at our child index. If that's less than 0, then we're going to set our child index to be equal to right child. Next, if our data at our parent index dot compare to our data at our child index is less than or equal to 0, we're going to break, and then we're going to set our data at our parent index and our data at our child index to be equal to the opposite. So data child index, data parent index. And then we're going to set our parent index to be equal to child index, and then we're going to return front item. So that was kind of a lot. Let's break it down real quick. So we have a generic class priority queue that can be any type. And we're giving it the iComparable interface so that it knows how to compare itself to other items. That's kind of where the priority part comes in. Smaller numbers, higher priority. So if we walk through in queue, we start out by adding a new item. And to make sure our index math works out, we're creating a child index and setting that to be equal to data.count -1, because we're using a list, but it kind of works like a binary heap. So the child index is going to be the index of the new item that we just add. And then we're going to loop through our list until our new item is at the root. And then we're going to calculate the parent index using the heap formula, which is this. But we only wanted to actually get to the root if it belongs there. So what we're going to do is we're going to check to make sure that the child is greater than or equal to the parent. If the child is greater to or equal to the parent, we can stop. We don't need to keep bubbling it. And then this right here is the bubbling. This swaps the child and the parent. And then we move on up. So what this will do is it will give us a list where things are sorted in order based on some value that we give it. So when we get the first item in our priority queue, it's always going to be the highest priority item. Dequeue is going to remove that item, but it also needs to make sure that the rest of the list still works. So it's going to bubble down and make sure everything is where it belongs after we remove that item. That's what all this is doing. Next, we're going to go back to Grid Manager, and my goal here is to get rid of system.link. If we don't need to use a namespace, we shouldn't use it. So we're going to start out by changing our open list from a list. We're going to say var open is equal to a new priority queue of type tile. Then we can get rid of open.add. And what we're going to do is we also want to reset all of the tiles in our map. We want to reset their costs to make sure our pathfinding is working properly. So inside here, we'll loop through our map. We'll do t.cost or t.gcost is equal to int.maxValue. t.hcost is equal to 0. And t.parent is equal to null. Now these we can keep the same. And then we will do open.enqueue start. Okay, so to keep it easier for you guys to follow and for my brain to organize it, we're just going to get rid of everything inside this while loop and type it all out. So we'll do tile current is equal to open.dequeue, and then if current is equal to end, then we're going to return retrace path, start and end. Now we're going to add current to our closed hash set. Next, we're going to do a for each loop. So for each tile neighbor in get tile neighbors, we're going to pass in our current dot grid position and true. If closed dot contains neighbor, we're going to continue. We're going to skip it if it's already on our closed list. We don't want to revisit things we've already done. Now we're going to do if our neighbor dot is occupied and neighbor is not equal to ignore occupied, then we're going to continue. So that right there might throw you off a bit. And basically what I want to include here is, do we want to have the start tile factored into our pathfinding? It could cause problems. And when I was testing, it did in fact cause problems. So at the top, we're going to pass in another argument called tile ignore occupied and initialize that to be null. So if we want to ignore a specific tile, we can pass it in to ignore it. Next, we're going to create an int called tempg. This is going to be equal to current.gcost plus our neighbor.moveCost. And then we're going to do if tempg is less than our neighbor.gcost or neighbor.parent is equal to null. Then we're going to set our neighbor.gcost to be equal to tempg. We're going to set our neighbor.hcost to be equal to getHeuristic. We're going to pass in our neighbor and our end. Now we're going to set neighbor.parent is equal to current. And then we'll do open.enqueue neighbor. So that's it for our grid manager. We did a lot, sort of. I mean, it felt like a lot. But we cleaned up these algorithms to make them a little more efficient, to make them cleaner, easier to read. And that should help us out quite a bit with efficiency in the long run. Now we want to hop on over to our tile script. And the first thing we're going to do is add the system namespace. So using system. Now we're going to add an interface. It'll be the I comparable of type tile. This is going to make it so that our priority queue can actually compare our tiles. And we need to implement that interface. So down at the bottom, we're going to create a public int called compare2. We'll pass in a tile called other. We're going to do int compare is equal to fcost dot compare2 other dot fcost. Then we're going to do if compare is equal to 0, then compare is going to be equal to hcost dot compare to other dot hcost, and then we're going to return compare. So if you remember, the code we had originally using lambdas basically did this. It checked first if the fcost was correct. If they were the same, then it would compare the hcost. So this is doing that same thing, except now it's doing it as it enters a list and not as part of the pathfinding. Now that that's been implemented, let's hop back to our grid manager actually, because I want to clean up our get closest to tactile function. So right now we have 2 for each loops in here, and it's kind of unnecessary. We don't need to be looping through every tile multiple times because we're already looping through every single tile on the map right here. So there's no reason we need to. So we're actually going to get rid of this list altogether. Instead, we're going to create a tile reference called target tile and set this to be equal to get tile target.grid position. And then we're going to create another tile reference called closest tile, set that to be equal to null, and then int best distance is equal to int.max value. So we essentially move these up to the top, and we're going to get rid of all of this because now we're going to do for each tile in map. We're going to do if not tile dot in move range. If the tile is not in the move range or the tile is occupied, and then we're going to continue. We're going to skip it. Next, we're going to create an int called distance to target. This is going to be equal to get heuristic. We're going to pass in our target tile and our tile. And then if our distance to target is greater than attack range, then we're going to continue. We're going to skip. Now we're going to change distance to attacker from a float to an int, and the rest of this will be the same. So that cleaned up our get closest to tactile significantly. So we can save that. And that is officially the last thing we need to do in our grid manager. So next we're going to tackle our player script. Now, find any object by type is great and all, but if we can avoid it, we're going to. So inside start, we're going to do grid manager, or if grid manager is equal to null. So if we don't have a grid manager, then we will try to find one. But we only want to try to look for it if we don't have one. Next, we're going to modify change selected unit. So underneath selected unit, we're going to create a tile reference called unit tile. And this is going to be equal to grid manager dot get tile. We're passing in our unit dot grid position. And then we're going to do unit tile dot select tile, which is going to yell at us for because that doesn't exist. And then we're going to highlight range, but we're going to replace get tile with our unit tile since we already have it. Just clean that up a little bit. Next, let's bounce over to our tile script and look at on pointer exit. I love my ternaries, but we can make this easier to read. So instead of doing that, we're going to instead do if selected tile equals this, then we're going to return. We're going to bounce out. Otherwise, if in move range, then we're going to change color to color.cyan. And we'll do else if in attack range, we'll change color to color.red. And then our final else is going to be change color to our original color. So it's not as compact as our nested ternaries we had, but it's easier to read. If we're in the move range, we're cyan. If we're in the attack range, we're red. Otherwise, original color. Next, we have our select tile, which does exist. I just forgot about it. It's private, though, which is why it was yelling at us in the player script. So we're going to change it from private to public. Next, we're going to create a public grid manager called grid manager. And remember, it was yelling at us in our generate grid function because grid manager didn't exist. So now if we go back over there, you can see that little red dot disappear. because now grid manager exists. So let's clean up on pointer down. We can get rid of this grid manager reference because we've got a global one now. We're going to create a unit reference though, called selected. And this is going to be equal to player.selectedUnit, which is going to make it so that we don't have to type out player.selected every time. So we're going to do if selected is equal to null or selected.isMoving, we're going to return. And we're going to do if we're not in the move range, so in move range, then we're going to return. So if we don't have a selected unit, or the selected unit is moving, or we aren't currently in the move range, we're going to bounce out. Next, we're going to create a tile reference called start tile. That's going to be equal to grid manager dot get tile selected dot grid position. And I'm basically going to get rid of the stuff we have in here currently because we're replacing it. Anyway, so next we're going to create a list of tiles called path, and this is going to be equal to our grid manager dot get path. We'll pass in our start tile, this tile, and start tile as the one to ignore. And it's going to yell at us because we aren't using system.collections in here, so we have to add that after. We're going to do if path equals null or path.count equals 0. Then we're going to return. Then we're going to do int total cost is equal to 0. And then for each tile t in path, we're going to do total cost plus equals t.move cost. And then if our total cost is greater than our selected dot movement left, we're going to return. So what we're doing here is we're essentially taking some work off of the unit. So basically what we're doing is we're checking to make sure that the path is valid, that we have the ability to move to wherever we're trying to go. Once we check to make sure the path is valid, we're going to do selected dot move to path. Then we're going to select tile, and then we're going to do grid manager dot reset grid highlights. So let's go to the top and add that namespace. So using system.collections.generic, that will allow us to use lists. Now it's yelling at us because move to doesn't actually take a path. It takes 2 positions, but we're going to change that momentarily. So let's hop into our unit script and go to handle movement. There's a lot of grossness happening in here. So let's get rid of it so it's easier to see what's happening. If we are not moving, so not is moving, or path is equal to null, or path.count is equal to 0, then we're going to return. Next, we're going to set our transform.position to be equal to vector3.move towards. I'm going to do transform.position, target position, then our move speed times time.delta time. Next, we're going to make our distance calculation a little nicer. So if our transform.position minus our target position dot square magnitude is less than our stopping distance times our stopping distance, because we've got a square, because square magnitude essentially makes it so we don't have to square root it, whereas vector3.distance does. So we're taking out a square root calculation, which is slower than just multiplying. So if that is true, if that's the case, we're going to set our transform.position to be equal to our target position. And then we're going to set movement left minus equals path at index 0 dot movement cost. And then we're going to do path dot remove at index 0. And then if our path.count is greater than 0, then we're going to do target position is equal to path at index 0 dot transform dot position, and our grid position is equal to path at index 0 dot grid position. Otherwise, so else, we're done moving. So is moving equals false, and then owner dot change selected unit this. So we're going to reselect this unit. Next, we're going to modify move to. We're going to expand it significantly. So we're going to change it. Instead of accepting a vector 3 and a vector 2, we're instead going to make it take a list of tiles called new path. So in our return function here, we're going to add some conditions. If new path is equal to null, or new path.count equals 0. Then we're going to bounce out and return. Next, we're going to get rid of these 3 lines, and we're going to do tile called start tile. This is going to be equal to owner.gridManager.getTile. We're going to pass in a grid position. Then we're going to set start tile dot is occupied to be true or false. We got to make sure we're checking the occupants here, else things are going to get real weird real fast. Then we're going to create another tile. So tile, this will be our destination tile. This is equal to new path at the index of new path.count -1. And then best tile, or destination tile, dot is occupied equals true. So we're going to remove our occupancy from our start tile and put it on our destination tile. Next, we're going to set our target position to be equal to path index 0. Next, we're going to set our path to be equal to a new list of tiles. We're going to pass in new paths for that list. Then we can set our values. So target position is equal to path index 0 dot transform dot position. We can set our grid position to be equal to path index 0 dot grid position. And we can set is moving to be equal to true. Lastly, let's modify on pointer down. So if owner is player turn, so if it's the player's turn, change selected unit to this and then return. We don't want to process anything else after that. And then because we're going to overhaul this, let's get rid of it. Make it easier for you guys to follow. Unit, player unit is equal to player selected unit. And then if player unit is equal to null or player unit is moving, we're going to return. Then we're going to grab those tiles. So tile, unit tile is equal to owner dot grid manager dot get tile. We'll pass in our grid position. Then we're going to grab our tile, call it attacker tile, and set this to be equal to owner dot grid manager dot get tile. We'll pass in player dot selected unit dot grid position. Now we're going to grab an int called get or int distance and set that to be equal to owner dot grid manager dot get heuristic. We'll pass in our player tile or our unit tile and our attacker tile. And then if distance is greater than player unit dot attack range, then we're going to return. And actually, I forgot that we stored that as a reference. So instead of doing player dot selected unit, we can just do player unit when we get the attacker tile. After that, we're going to grab a tile reference called closest attack tile. And this is going to be equal to owner dot grid manager dot get closest attack tile. We're going to pass in this and our player unit if closest attack tile is equal to null, then we're going to grab our player unit and tell it to attack this unit. And then we're going to return. Because again, we don't want to process anything after we perform our action. Next, we're going to grab a list of tiles called path. Set to be equal to a new list. Next, we're going to create a list of tiles called path and set this to be equal to owner.gridManager.getPath. We're going to pass in our player tile, or our unit tile. We're going to pass in our attacker tile and our closest attack tile. If path is equal to null, or path.count is equal to 0, then there's no path available. We're going to try to attack. So player unit dot attack this. Otherwise, if we do have a path, then we're going to do player unit dot move to path. All right, after all that, save everything, head back to Unity. So once you're back in Unity, let's check our console, make sure nothing super big is wrong. Looks like we forgot to change the tile renderer access modifier. So let's go to tile, go up to tile renderer, make that public, save that, and head back to Unity. So in Unity, let's make sure we're assigning our grid manager references. So on player and enemy, I'm dragging in grid manager. UI manager, we don't need to do anything with. Turn manager, we don't need to do anything with. Our units should be all set. And our grid manager, we need to assign the material. So let's go to materials. I'm just going to drag in the light tile material. Doesn't really matter. So save the scene and let's hit play. So I'm going to see we still have an issue here. So let's go to our prefabs because I know what one of the issues is. Let's open up our tile prefab. Select our tile. Tile renderer isn't showing up because we're not assigning it. So let's grab our tile art and drag that into the tile renderer slot. And that will make sure at least our grid will instantiate. So if I hit play now, our grid shows up. And something that's interesting is because of those changes, our map is now flipped, which is fine. It's not a big deal. I just think it's interesting that the little tweaks we made to generate grid also flipped the colors. So we can move around. Everything is still happening. I can end my turn, end the enemy's turn. So not a whole lot has changed. Everything basically looks the same, but our code is now easier to read. It's also stronger and less prone to errors. And it should be able to run smoothly even if we have huge maps and movement ranges. So that's another reason I kind of wanted to do this is if we have a unit with a huge movement range, or we have a map that's, I don't know, 25 tiles by 25 tiles, or even massive, like 100 by 100, our pathfinding and everything should still be able to run without any hiccups. Whereas before, because it wasn't super efficient, we were doing all kinds of messy things, it wasn't efficient, and we would have started to see some hiccups with larger maps. So in the next video, we'll actually get something visual rolling by making it so the enemy can move their units around too. That's all for today though, so if you like this video, hit like and subscribe to help out the channel. Let me know in the comments, what kinds of errors have you had to deal with so far? I remember when I was watching a bunch of tutorials, null reference exceptions were the bane of my existence. Now it's out of bounds indices. As always, thanks for watching. I'm Alex with Serious Goose Games, and I'll see you on the next one.